Hello and welcome to the channel. There is a number of things attributed to Napoleon I, also known as General Bonaparte, to which the self-proclaimed Emperor of France has no relation at all. Among those are popular Napoleon cake and a palindrome, Elba was I, air, I saw Elba, which appears the same whether read as usual from left to right or in the opposite way, from right to left. For someone who doesn't know, air is an archaic English word for before, related to time. Elba is an island between Corsica and continental Italy, now belonging to Italy, where His former Majesty was exiled to serve as the governor by the Treaty of Fontainebleau after his abdication in 1814. What is really amazing about that, being fluent in Italian and French, Napoleon didn't speak English even after spending 6 years as a British prisoner at St. Helena Island, while this phrase he allegedly said before becoming a British prisoner. This video is about the problem known from the middle of 19th century as Napoleon's problem, while its real authorship is disputed. Here is what Napoleon's theorem is about. Take an arbitrary triangle and construct equilateral triangles on all sides of it. The triangles can be constructed either all outward or all inward. For simplicity, I will use term outer case when the triangles are constructed outward and inner case when construction is done inward. Then we find the centers of all constructed equilateral triangles. These will be centroids, incenters, circumcenters, orthocenters, and a number of other centers, all in one. The Napoleon theorem states that if we connect all these centers, we get another equilateral triangle. The new equilateral triangle is named Napoleon's triangle. To summarize it, if equilateral triangles are constructed on the sides of any triangle, either all outward or all inward, the lines connecting the centers of those equilateral triangles themselves form an equilateral triangle. This is a photocopy of what seems to be the first known published proof of the Napoleon theorem, dated back to 1826. The image is taken from Wikimedia, where it is listed as public domain material. There are actually two proofs here. The first proof is purely geometrical, based on congruency and similarity of triangles. The second proof is computational, involving geometric formulae and trigonometry. Nowadays, numerous ways to prove the theorem are known, but these ones still appear to be the simplest. Someone may find surprising that though the almanac is named The Lady's Diary, all the contributors mentioned here are men. I will use the second computational solution by Mr. Mason from Skelton. Firstly, because it appears simpler to me, secondly, because it gives some useful results. However, someone may find the second proof less impressive than the first one. 3 more names are mentioned here regarding the second solution who use the same principles as Mr. Mason. I can't even imagine how the authors could be surprised to find out that their names would be mentioned in the 21st century. And another name has to be mentioned here, Mr. W. Rutherford from Woodburn, who suggested this problem. The problem appeared in the previous release of The Lady's Diary, published in 1825. He is better known as William Rutherford, English mathematician and editor of various mathematical publications. In 1824 or 1841, according to other sources, he established a new world record by calculating 208 decimal places of number pi. Later it was found that only 152 digits of his result were correct, so the record is now disputed. However, in 1853, he established a new world record with 440 decimal places of pi, and since I haven't seen any claims regarding inaccuracy of this later result, I assume it is correct. We start with the outer case. ABC is the original triangle. Small letters ABC are used for the sides of this triangle. PQR are the centers of constructed equilateral triangles, as shown in the drawing. The approach is pretty straightforward. We compute the value of a side forming the Napoleon triangle and show that the value doesn't depend on the selection of the side. Take side PQ, for example. Its length can be computed from triangle APQ using the cosine rule. Name it Formula 1. Try to continue from here. Find the lengths of segments AP and AQ, which are the circumcircular radii in equilateral triangles. There are several ways to calculate them. The above-mentioned Mr. Mason from Scouten suggests the following. Draw PH perpendicular to AC, where H is the point where PH and AC meet. Since P is the circumcenter, PH must be the perpendicular bisector to segment AC. This means that H is the midpoint of segment AC. Therefore, AH equals half of AC, which is B over 2. At the same time, P is the incenter of the equilateral triangle. Therefore, AP is the bisector of an angle of 60 degrees. This means that the value of angle PAC is 30 degrees. From right-angled triangle APH, we find AP is AH divided by cosine of 30 degrees, which is B over 2 divided by square root of 3 over 2, which is B divided by square root of 3. In the similar way, we get AQ equals C divided by square root of 3. We also need to find cosine of angle PAQ. Angle PAQ can be represented as the sum of three angles, PAC, CAB, and BAQ. As we already know, angles PAC and BAQ both equal to 30 degrees. CAB is an inner angle of triangle ABC. Denote its value with letter alpha. So we get that the value of angle PAQ is alpha plus 60 degrees. Now we apply the formula of cosine of sum to angle alpha plus 60 degrees and substitute the values for cosine and sine of 60 degrees. This gives formula 2 for cosine of angle PAQ. Can you find a glitch in the expression for angle PAQ? This is what was overlooked by the author and probably by the editor of the almanac as well. If alpha is more than 120 degrees, then the value of alpha plus 60 becomes more than 180 degrees. This is inappropriate for an inner angle of a triangle. The drawing for this case shows that the actual value of angle PAQ is 300 degrees minus alpha, which complements angle alpha plus 60 degrees to 360 degrees. Fortunately for us, 360 degrees is a period of cosine, and in addition, cosine is an even function. Therefore, cosine of 300 degrees minus alpha is the same as cosine of alpha plus 60 degrees. If alpha is exactly 120 degrees, then A, P, and Q belong to the same line, so PQ is just the sum of AP and AQ. However, the general case covers that, so it doesn't need to be considered separately. So I corrected the value of angle PAQ. However, as we've seen, it doesn't affect its cosine, and we continue. So we substitute the values of AP, AQ, and cosine of angle PAQ into the equation 1. 2's in numerator and denominator are cancelled out, and in order to get rid of the fractions, we multiply both sides of the equation by 3. This gives formula 3. Our next step is getting rid of alpha. Think of how it can be done. Look at the last term in the right-hand side of the formula 3. Doesn't it ring the bell? Of course, there is a formula for the area of triangle, which is half of BC times sine of alpha. Following Wikipedia, we will use capital delta for the area of triangle ABC. So we get BC times sine of alpha equals 2 times delta. We also have cosine of alpha in the formula. To get rid of it, we again use cosine rule, this time for side BC in triangle ABC. Substitute the values and find that minus 2bc times cosine of alpha equals a squared minus b squared minus c squared. To get the corresponding term in the equation 3 looking exactly like that, we multiply both sides of the equation 3 by 2. Now we substitute the values of minus bc times cosine of alpha and bc times sine of alpha. Here we have similar terms which need to be merged. This gives a nice looking formula for 6 times pq squared. We only need to divide by 6 to get pq squared. Remember that delta is the area of triangle ABC, where sides A, B, and C appear symmetrically. The first term is also symmetric for A, B, and C. Since, using the terminology from the almanac, A, B, and C are involved exactly in the same manner in PQ, it is manifest that the same expression gives the values of other sides, PR and QR. Consequently, the triangle PQR is equilateral. For the side of outer Napoleon triangle, I will use N outer, N for Napoleon of course, and this will be formula number 4. So apart from proving the Napoleon's theorem, we also found the length of the sides of the Napoleon's triangle, and that's the reason why I chose this proof. Now we can also find the area of the Napoleon's triangle. Since it is equilateral, the area of Napoleon's triangle is n outer squared times square root of 3 divided by 4. We substitute the value of n outer. The second term is simplified as square root of 3 times square root of 3 gives 3, which cancels out with the denominator, and we get quite compact formula 5 for A outer. And here are 3 formulae for delta, the area of the original triangle ABC. And as expected, A, B, and C appear symmetrically here. We move to the inner case. For a given triangle ABC, we construct inward the following equilateral triangles. On the side AC with center in point P, on the side AB with center in point Q, and on the side BC with center in point R. We need to prove that triangle PQR is equilateral. Again, we evaluate the length of segment PQ from triangle APQ using cosine rule. The formula 1 is the same as for outer case, so I just copied it here. However, the value of cosine of angle PAQ is different from the outer case. We have angle PAQ equals angle PAC minus angle QAC. Since P is the incenter of equilateral triangle built on side AC, angle PAC equals 30 degrees. And we get formula 6 where angle QAC still needs to be evaluated. We have angle QAC equals angle CAB minus angle QAB. Angle CAB is an inner angle of triangle ABC and its value is alpha. Point Q is the incenter of triangle built on side AB, therefore angle QAB equals 30 degrees. So we get the expression for angle QAC and substitute it into formula 6. This gives angle PAQ equals 60 degrees minus alpha, which is valid in case alpha is no more than 60 degrees. For alpha bigger than 60 degrees, the value will be opposite. If alpha is exactly 60 degrees, the value of angle PAQ is 0. So in this case, A, P, and Q are collinear, and the length on segment PQ is just the difference between AP and PQ. We see that in inner case, angle 60 degrees behaves similarly to angle 120 degrees for the outer case. In general, the value of angle PAQ is the absolute value of alpha minus 60 degrees, while the lengths of AP and AQ are the same as for the outer case. We substitute the value of angle PAQ and the lengths of segments AP and AQ into formula 1. And again, the evenness of cosine gives us a favor, as we can drop the signs of absolute value for the angle PAQ. Now we have difference instead of sum for cosine. Therefore, after we distribute and multiply by 6, we get the last term with minus. This results in having minus for delta in the formula for the side and the area of the inner Napoleon triangle. Formula 6 and 7. We've seen that angle 60 degrees is special for the inner case. Consider the case when all angles of the original triangle are 60 degrees. In other words, the original triangle is equilateral. It can be easily seen that an equilateral triangle drawn inward at any side of the original triangle matches the original triangle. Therefore, the centers of all three constructed equilateral triangles coincide with the center of the original triangle. So the Napoleon triangle squeezes into a single point. Indeed, when sides A, B, and C are equal to each other, the formula for an inner gives 0. In the case of a non-equilateral triangle, at least one of the angles will be different from 60 degrees, so the bisectors will not match, and the centers will not match either. In this case, an inner will be positive. This leads to the following inequation, where we can move the second term to the right-hand side and multiply by 6. This brings inequation 8, where, as we've seen, equality holds if and only if A, B, and C are equal to each other. The inequation 8 is named Weissenberg's inequality. It was published by Austrian mathematician Roland Weissenberg in 1919, 93 years after the publication of the proof in Lady's Diary. However, this is most probably an independent result, as there are numerous ways to prove it. A more precise inequality was obtained by two German-born mathematicians, Hugo Hadwiger and Paul Finzler, who already lived in Switzerland when the result was published in 1937. And here again, the equality holds if and only if A, B, and C are equal to each other. Here is a summary of our results obtained so far. By subtracting equation 7 from equation 5, we get A outer minus A inner equals delta. This can be written as A outer equals A inner plus delta. From which it follows that the area of outer Napoleon triangle is more than the area of the inner Napoleon triangle. Also we see that the area of outer Napoleon triangle is no less than the area of the original triangle. Here the equality holds if and only if the area of the inner Napoleon triangle is 0, which, as we've seen, takes place if and only if the original triangle is equilateral. Indeed, it can be easily seen that if the original triangle is equilateral, the corresponding outer Napoleon triangle can be obtained by 180 degrees rotation of the original triangle around its center. Then, when you build outer Napoleon triangle for the constructed triangle, you get back the original triangle. The following fact isn't usually considered as a part of Napoleon's theorem, but it will be an essential addition to it. The centers of both inner and outer Napoleon triangles coincide with the centroid of the original triangle. Just a reminder that for a triangle, centroid is the point where the medians meet. The coincidence of centroids can be proven using either vector algebra or complex numbers. In this video, I am going to show you an elegant and purely geometrical proof by a humble and bright Math.Stack Exchange user known there as CR001. Unfortunately, the user keeps an air of mystery about their personality. One useful remark before proceeding to the proof. There is actually no need to draw equilateral triangles in order to find the Napoleon triangle. We know that the center of an equilateral triangle is equidistant from endpoints of each side and makes 30-degree angles with the sides. So we just draw isosceles triangles with base angles 30 degrees for each side of the original triangle, and the three apices P, Q, and R for the constructed isosceles triangles form the Napoleon triangle. Now to the proof. Let again H be the midpoint of segment BC. As we've already seen, PH is perpendicular to BC. This time we continue segment PH to point F so that PH equals HF. It can be easily seen that P and F are symmetric against line BC. Therefore, CF equals CP and angle FCH equals angle PCH equals 30 degrees. Now consider triangle CFP. As we've seen, it has two equal sides, CF and CP, and the included angle FCP equals 60 degrees. Therefore, triangle CFP is equilateral. Consequently, PF equals CP and angle CPF equals 60 degrees. In the same way, it can be proven that triangle BFP is equilateral, so that PF equals BP and angle BPF is 60 degrees. Now consider triangles PCQ and PFR. These triangles have two pairs of equal sides. It was proven that PF equals CP. Also, PR equals PQ as two sides of the Napoleon triangle, which, according to the Napoleon theorem, is equilateral. What remains to prove is that the included angles CPQ and FPR are equal to each other. So we write angle CPQ plus angle QPF equals angle CPF, which, as it was shown before, equals 60 degrees. Another equation, angle FPR plus also angle QPF equals angle QPR, which is also 60 degrees as an inner angle of the Napoleon triangle. It comes out that angles CPQ and FPR are equal to the same value, therefore they are equal to each other. Finally, we can write that triangle PCQ equals triangle PFR by side angle side rule, from which it follows that CQ equals FR. Further on, since triangle CQA is isosceles, we get CQ equals QA. Comparing two last equations, we conclude that QA equals FR. In the similar way, we prove that triangle PQF equals triangle PRB, from which it follows that QF equals RB. This time we consider isosceles triangle ARB and conclude that RB equals AR and then QF equals AR. Now the attention goes to the quadrilateral FQAR. It has been proven that its opposite sides are equal to each other. QA equals FR and QF equals AR. Hence, FQAR is a parallelogram, and their diagonals AF and QR meet at their midpoints. Using letter G for the point where the diagonals meet, we can write that G is the midpoint for both AF and QR. Yet another triangle to be considered, triangle PFA. H is the midpoint of side PF. G is the midpoint of side AF. Therefore, GH is the midsegment. Hence, it is parallel to the third side AP, and its length is half of the length of AP. Another quadrilateral to consider, PHGA. We know that this is a trapezium, as GH is parallel to AP. Let O be the point where its diagonals AH and PG meet. Due to the similarity of triangles GOH and AOP, we have AO to OH equals PO to OG equals AP to GH. The last ratio, as we found before, is 2 to 1, therefore all the others are the same. Only few lines remain on the page, but that will be enough. Since H is the midpoint of BC, AH is one of the medians of triangle ABC. Point O divides the median in ratio 2 to 1. Therefore, O is the centroid of triangle ABC. At the same time, G is the midpoint of segment QR. Therefore, PG is one of the medians of Napoleon triangle PQR. Point O divides PG in ratio 2 to 1. Hence, point O is the centroid and therefore the center of Napoleon triangle PQR. So this beautiful proof has come to the end. For the inner case, the proof is exactly the same, only the drawing is different. As a memory exercise, I suggest to pause the video and try to recollect the proof. And here is the proof. I just copied it from the previous page. The last topic in this video is Pether-Douglas-Neumann theorem, often abbreviated to PDN, discovered independently by Czech mathematician Karl Pether in 1908, American J.S. Douglas in 1940, and German-born Bernhard Neumann. Professor Neumann, or maybe Newman using English pronunciation rules, spent most of his mathematical life in Australia, so I will take a few minutes telling about him. For moving straight to the theorem, just skip to the next chapter in the video or hit a timestamp link in the description. Bernhard Neumann was one of the first Jewish refugees from Nazi Germany who got refugee status in UK in 1933. He defended his second PhD at the University of Cambridge in 1935. Paper Some Remarks on Polygons, containing the result now known as Pether-Douglas-Neumann theorem, was probably written at the start of 1940 when Bernhard worked as a lecturer in Cardiff, Wales, considered unliable for serving in the British Army. The paper was submitted to the journal Composita Mathematica, published by Cambridge Press, and was planned to appear there in May 1940, but it didn't. In October 1941, when the paper was finally published in the Journal of London Mathematical Society, its author already served in the British Army, from where he demobilized in 1943. After the war, he published numerous influential papers on various subjects of mathematics, won several awards, and was elected Fellow of the Royal Society in 1959. However, in 1962, he suddenly takes the challenge and moves several thousand miles away, to the end of the world, to Australia, where he lived until his death in 2002, at the age of 93. He worked for the Australian National University and CSIRO. In 1994, he was appointed Companion of the Order of Australia. He chaired the Australian Mathematical Olympiad Committee from its formation in 1980 till 1986. At the same time, he participated in organizing international mathematical Olympiads, one of which, in 1988, took place in Sydney. In 1997, in recognition of his contribution to mathematical learning in Australia, the Australian Mathematics Trust commissioned his portrait from twice Archibald Prize winner, Australian artist of Hungarian origin, Judy Kassab. According to the other sources, the portrait was the initiative of Australian mathematician Cheryl Prager, who donated money for painting the portrait. This photograph was taken at 11th of November 1997, after the portrait was unveiled. I wonder if Professor deliberately hides his hands, and someone commented that the hands on the portrait look a bit odd. However, Professor Neumann liked the portrait, and when asked about the artist, replied, "She talked all the time and asked me questions, and I talked all the time. So the portrait is not a photograph, it's myself." Now to the theorem, which states the following. I placed some comments in brackets in hope it will help. I suggest to read and get a feeling of it. Then I will try to do my best in translating into plain English. So, given an arbitrary polygon having n vertices, k is a whole number in the range from 1 to n-2. Each value of k can be used once and only once, but the order of values is arbitrary. This gives n-2 repetitions of the process consisting of the following. At each side of the polygon, draw an isosceles triangle having the apex angle of 2 pi k over n radians or 360 k over n degrees. The apices of the constructed triangle form a new polygon. The next step applies to this new polygon with a different value of k. The theorem states that after all n-2 steps are complete, the result is a regular polygon, that is, a polygon where all sides are equal to each other and all angles are equal to each other, and the center of this regular polygon coincides with the centroid of the original polygon. The proof can be found in Wikipedia. It is based on complex numbers used as vector coordinates. The article claims the proof to be easy, however, I don't think so. In addition, I find it too boring for this video, which is already much longer than I originally expected. So I take the liberty to skip the proof here and bring my sincere apologies for that. Before I'm going to visualize the theorem on different polygons, two essential remarks. Remark number 1. Let beta k be the value of the apex angle. The range for k suggests that beta k is in the range from 2 pi over n to 2 pi times n-2 over n. This inequation shows that beta is positive and less than 2 pi, or 360 degrees. However, beta can be 180 degrees or more. Can an apex angle be like that? In general, not, but in this case it can be allowed by the following assumption. If beta is below 180 degrees, construct the triangles in usual way with beta as the apex angle. If beta equals 180 degrees, don't build triangles, just use midpoints of the polygon sides instead of apices. If beta exceeds 180 degrees, use 300 degrees minus beta as the apex angle, and build the triangles in the opposite way, meaning inward instead of outward or outward instead of inward. Remark number 2 is a sensational one. The centroid referred in the statement of PDM theorem is not what is usually meant by centroid. What is meant here is known as vertex centroid, and it is in general different from the center of mass, also known as area centroid. The definition of vertex centroid is much simpler than the one for area centroid. The coordinates of vector centroid are just the average of the coordinates of vertices. For a triangle, both centroids are located at the intersection of the medians. For a quadrilateral, the vertex centroid is the intersection of bimedians, lines joining the midpoints of the opposite sides. For a regular polygon, both centroids match its center. This quadrilateral is going to be used in one of the following chapters. To find the vertex centroid, we just connect the midpoints of the opposite sides. Vertical centroid is the point where the lines meet. The construction of a centroid is more complex, as it involves finding centroids of each triangle formed by either of the diagonals. Fortunately, this is irrelevant for PDM theorem. As you can see, area centroid in this case is different from vertex centroid. Value 3 for n corresponds to a triangle. n minus 2 equals 1, which means that k can be only 1, and there is no repetition. The value of the apex angle B1 equals 120 degrees. Therefore, both base angles are 30 degrees. As we already know, this defines the center of equilateral triangle constructed on the side of the given triangle. So, for n equals 3, Petrer-Douglas-Neumann theorem turns into Napoleon theorem. Take n equals 4, corresponding to a quadrilateral. Now k can be either 1 or 2. And we get beta 1 equals 90 degrees, which means constructing right-angled isosceles triangles, and beta 2 is 180 degrees, which means just taking the midpoints. N equals 5, a pentagon. 3 possible values for k, consequently 3 values for beta. 72 degrees, 144 degrees, and 2016 degrees. Value 216 is over 180, so we subtract 216 from 360 and get 144 degrees. For this value, the triangles are drawn in the opposite way. For n equals 6, that is for a hexagon, we get 4 values of beta. Beta 1 is 60 degrees, beta 2 is 60 times 2, which is 120 degrees, beta 3 is 60 times 3, which is 180 degrees. This means taking the midpoints. Beta 4 is 60 times 4, which is 240 degrees. This means that the apex angle is 120 degrees and the triangles are drawn in the opposite way. As we've seen, 2 steps are needed for a quadrilateral with apex angles 90 degrees and 180 degrees. According to the theorem, the angles can be applied in any order, and the triangles can be drawn either outward or inward. Here we have only 2 choices of order, either angle 90 degrees first or angle 100 degrees first. We will try both and start with drawing outward. So we take 2 already familiar to us quadrilaterals and again find their vertex centroids. And apply increasing order of angles to the left quadrilateral, decreasing order to the right one, applying the angle of 90 degrees. In case of 90 degrees apex angle, the apex is the intersection of the circumference built on the side as a diameter with the perpendicular bisector to the side. Instead, we can just draw 45 degrees base angles, of course. So we construct the isosceles triangle and do that for all sides. Then we connect the apices and get a new quadrilateral. Now we need to apply the angle of 180 degrees. To do that, we just connect the midpoints. And we get a square that is a regular quadrilateral. To find its center, we draw the diagonals, and the central square will match the centroid of the original quadrilateral. Now do that with the right quadrilateral in the inverse order. Applying angle 180 degrees, and then 90 degrees. And we again get a square with the center matching the vertex centroid of the original quadrilateral. This time we will draw the triangles inward. In increasing order of angles, 90 degrees, and 180 degrees. Now in decreasing order of angles, 180 degrees, and 90 degrees. In both cases we get squares whose centers match the vertex centroids of the original quadrilaterals. A pentagon requires 3 iterations, so there are 3 factorial or 6 ways to apply them. Of course, we are not going to try all of them, we will just use the increasing order of angles. The original image was downloaded from Wikimedia. The author calls himself Krishna Chandra NVN. It's a nice job and I only made it working for this video. Drawing outward will be the standard way, drawing inward the opposite way. This is how it draws better and looks better. As the first step, we draw isosceles triangles with the apex angle of 72 degrees outward. Connecting the apices gives the polygon for the next step. Now we apply the apex angle of 144 degrees and still draw outward. And we get the polygon for the last step, where we also use the apex angle of 144 degrees but draw inward. As expected, the result is a regular pentagon. I wonder if the authors of PDN theorem, at least one of them, ever tried their discovery in practice. It was possible at that time, though not as easy as nowadays. It could even happen that the result was first observed and then proven. We had demonstration for a triangle, quadrilateral, and pentagon. Let's do it for a hexagon. 4 steps, 24 permutations, but we will again apply increasing order of angles, drawing outward for angles below 180. To facilitate finding the vertex centroid, we present the equation for its coordinates as the average of triangle centroids. This suggests the following approach. Divide the hexagon vertices into 2 sets, 3 vertices in each. Find centroid for each set and connect the centroids with the line segment. The vertex centroid of the hexagon is the midpoint of the segment. This time I couldn't find anything relevant on the web, so please welcome the demonstration of my own. This is the last presentation in the video, everything should be clear by now. Just watch and have fun.